Yo, what's up, everybody? Welcome back. Today we are working on our image editor, and today's task is making a tiny page allocator. So the context here is that we have been working on this idea where we are trying to remove individual allocations from our image editor. Or individual frees, I should say. Individual allocations, still good, but for the most part, we're trying to get rid of individual frees. And the motivating case for this is I didn't like the idea that I had a bunch of like error cleanup code that was related to like memory management that was basically never run, and so kind of like completely untested. I just like don't like that idea. So instead, we're like, well, what if we say we don't free individual things, we free pools of things, and then the pools will always be freed, whether or not we're in the error case or the happy path. Like we're going to free pools, whether it's just going to be like whether or not we do it now or later, which means that like all of this stuff kind of goes away, and that concept has definitely been working. So if we look at our diff from when we implemented this concept of memory pools, we can grep get diff from here, and we can maybe grep for lines that were added with the word error defer in it, and we can count those. So maybe this is wrong because it sounds like yeah, it doesn't look like this is doing what I want. Yeah, so get diff. First of all, this is for error defer. Hold on. And then can we look for things that start with a minus and then say error defer? Yeah, that's working. Maybe I spelled error defer wrong. So we've removed 153 of them, and we've added 9. That's a pretty big win in my books. So we've definitely like reduced the like error handling complexity of this thing. But it is coming to cost. It's coming to cost. So the way we did this is we were saying like, you know, typically when people talk about like memory pools in like C and stuff, I hear the word arena a lot. And what arenas do is you kind of like pre-allocate this chunk of memory, or maybe you allow like you have some sort of like grow policy where it can like map more pages from the system, but like you have some pool, right? And you have like a pointer at the beginning of this pool. And every time you allocate something, all you do is you bump the pointer forward. Boom, 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 boom. And when you free, you know, hand wavy, you just do nothing, right? Because the idea is if this thing is like kind of short lived, then you can just free the pool every once in a while and it's like fine, right? Like you could imagine a case where you would be doing this is like every frame you spawn, you like reset this guy and you like pass him around to a bunch of people and they like move the pointer forwards and then you go, okay, frame's done, we reset, right? It works great for that idea. Or like you're servicing an HTTP request, and for every connection, you spawn one of these like scratch allocators, and you like bump them. You use it for the lifetime of the connection, and then when you finish handling the request, you reset it. Right? That works well for that. But our case is like a little different, where we have like kind of like a big application. It was kind of designed with the idea that we're going to be freeing memory at times, and it doesn't really work that well for us. So what we've done instead. Is we have created some sort of similar system where you can still use a general purpose allocator, right? Let's see if we can find an example. So like in font storage, right, for every font that we load, we push this thing into an array list. Or I guess object storage is a better name. So for every image in our entire image editor, we will put it in this object storage. And this object storage is like a hash map, right? This hash map is going to change size, right? As we add and remove elements, it makes sense for the hash map to try to like grow and free memory as it needs, right? So this idea of the arena doesn't really work. What we did instead is we went through this experiment where we implemented a couple allocators just to kind of see how they work, right? And the workflow is essentially you have this call to the system, mmap on Linux. I think it's called virtual alloc on Windows, but like some similar concept, where you basically say, give me pages of memory. It works in pages, where pages are, okay, can you like shut up? I'm just gonna time you out, you're being annoying. Where pages are like big-ish blocks of memory, right? So these guys are gonna be like 4K, approximately. They'll be different, like on like ARM. I think on like ARM 64, they're 16K or something. There's sometimes like they're not even like a fixed size; they're like configured by the system. But we'll say 4K for now. And when I call like malloc in C, or I call like alloc in Zig, this will basically say, do I have any pages? If so, cool. We'll split this guy up into smaller segments, and we'll track them with some sort of like, you know, intelligent data structure, so that we can quickly look up, you know, size of blocks that we've allocated, size of blocks that we've freed, et cetera, et cetera. But like kind of like the main takeaway here is that this is the base unit, right? So what we did to make our pools is we made we took like a page allocator, and then we put one thing in between it that says like what pages are allocated. So we just like write down what pages have been allocated, and then instead of like freeing from our general purpose allocator, we just like nuke all of these pages at once, right? So what we have is like we have a page allocator that has like a general purpose allocator in here, and he also has like an arena, because like why the fuck not, right? Because like in some cases like an arena fits really well, in some cases we still need to use this general purpose allocator. The general purpose allocator has like a little bit more overhead because he has to do free tracking, but he has the advantage of being able to free memory and be able to reclaim it later, right? Now the problem is with this scheme, we've kind of said we don't free individual memory anymore. We're like, we've transcended that. We're too cool to free individual blocks of memory. But that means that we need to make one of these pools of memory for like every lifetime in the system, right? So if every single object that we have has one of these like allocator elements that has two allocators underneath them with the like page allocator tracking. And that's the problem here, is that since these guys only work in page units, it means that every single object in our entire system, like everything that has its own lifetime, probably has an overhead of like 8K, right? One for each of these allocators. Ew, gross, 8K? When like, what are we even like using this thing for, right? If we look at like a file system object in here, i.e. like if we run this guy and we look at, really quickly, we just look at an example, right? So each of these guys is like an object. And what is really being stored in this guy? Well, we look at his properties here, and it's like probably like the file name in here and like his like name in the system, right? We can kind of confirm that really quickly. So load image, I think we call this. And here we create a file system object. This guy has like a source, which is allocated, plus object name, which is allocated, right? So it's literally like two things. And so in reality, if we like look at one of these guys, hold on, I don't know why it rebuilds every time, it's kind of annoying, but whatever. Banister.jpg, right? So we have banister.jpg twice here, right? And that is taking up 4 to 8K. Doesn't make sense. That's way too much, right? And so what I'm thinking is I want something that fits this idea. It feels really good. Kind of like overall usage of the thing is like mwah. But my only problem is that this is too big. These pages are fucking too large. I don't want 4K per page. And so what I'm thinking is I want to make a tiny page allocator. So basically something that sits between kind of here and here, and let's just say, you know what? Like each of these pools that we make, we'll just allow them to allocate blocks of like 256 bytes instead of 4K. The only reason that there's this 4K limitation, well, I'm making this up, but my understanding of why there's this 4K limitation is because you have this thing in your computer memory management unit, right? This guy is in charge of when like the CPU says like, you know, hand wavy, CPU's like, well, we're gonna gloss over like what the fuck is a CPU, right? But like, let's pretend that the CPU talks to the MMU. In reality, maybe this thing is like integrated, but like whatever. He says like, get me this thing at 0x1234, right? This guy has to reach out to like physical RAM and figure out like on the bus, the little bus here where he talks to these guys. Choo choo. I guess buses don't say choo choo. They say meep meep. Like what address is this on the bus? And so what they have is they have these things called like, I think they're called page tables. Page tables. And it's basically some structure that says for every single like chunk of virtual addresses, where does that map into like the physical RAM in my computer, right? And so like you could see why having a page size of like 4K, CPU be like, hey MMU, how you doing? Yeah, exactly. You could see why having like a bigger block here makes sense, right? Because like the larger the block is, the smaller the data structure is, right? But we don't have this restriction. We just have like a list of pages that we've allocated. So I think that we're totally fine to just put a layer in between that like chunks up big blocks into small blocks. And that's what I want to work on is like, first we need to do that. And then we need to make sure that like our sub allocators know to ask for smaller blocks. And I think that we can get this down to like 128 bytes of overhead or 256 bytes of overhead instead of the current like 8K. So that's the plan. That's the plan. Christoph, thank you for the raid. Apologies for the lack of quick acknowledgement, but I was in the middle of talking and I wanted to finish my thought. But thank you for the raid. Hello, Christoph viewers. I hope you guys had fun over there. So let's get moving. Somebody's saying, sorry, I don't know, no Kiam. I think the reason is that they're 4K is that the 32-bit systems, there were 2 page tables, each 10 bits of indexes, and that leaves 32 minus 20, 12 bits is 4K. But like, I was trying to think like, why is like, I don't know why that was their design decision. This is my guess as to why they have smaller sets of indices, but I could be wrong. I kind of made it up. Okay. So let's get started with this idea of tiny page allocator. And surely this guy just wraps. He's going to like, what does he do? What does he do? We know that we are going to want blocks of sizes 2 to the power of small to 4K. Right? We know that we're going to be doing stuff in this range, right? Because anything bigger than 4K, we can just fall back on the real page allocator. That would work just fine. We also know that we are only going to have one of these for the whole program, right? We're going to initialize this one fucking time off rip, and we're going to pass them around to all of our sub allocators. We know that like allocations will only be powers of 2. Right? So we don't have to worry about the fact that somebody might ask for like 140 bytes. We know that they're going to ask for 128 or 256 or 512, right? And I think that we probably know that freeze should be relatively rare. Right? I think allocations may happen quite often. But like, I suspect, I mean, I could be wrong about this, but my gut feel for the way that our program runs is that like, we're going to allocate a lot on initialization, then like not do much. Hand wavy, right? And yeah, I mean, I could be wrong here, but so these are kind of like the constraints I'm thinking of. Now, we have previously looked at the idea of this thing called buddy allocator. So buddy lists. The basic idea here is it's a funny name, but the idea is essentially that you have one list for each block size. So in our case, we're gonna say like 256 chunk block, 256 byte blocks, 512, 1024, and 2048, right? This is kind of like all we need if we want our minimum size to be 256, because 4096 onwards are handled by the real page allocator, right? So we have these. And the idea is somebody asks for a 2048 block. So we get a 4096 block from the system, we cut it in half, we give one away, this goes to the user, and the other side goes into this. Then somebody asks for a 512 block, right? And we're like, well, we have this 2048 block right here, so we cut it in half, put one half in here, cut the other half in half again, and put one half in here, and then give the remaining 512 to the user. So this goes out, then we have, one of each of these. Then when somebody frees this guy, we go, okay, well, we got this guy back in, and we put him in the list, and we go, wait a second, these guys are right next to each other. These guys came from the same fucking block. And if they came from the same fucking block, we could like merge them and put them back in the 1024 block. And we go, wait a second, these guys are the same. So we kill these, put them back in the 2048, and we go, wait a second, these are the same. And we put them together and free it back to the system, right? That's kind of the idea behind the buddy allocator. We implemented something like kind of along these lines. We never did the merging stuff. And our constraints now are different than our constraints then. But I think that this is like a perfect fit. I think we can probably assume, based off of our constraints here. Hold on. Where were we? Sphalloc. So where do we write down our constraints? In here. So we also, an extra constraint here is we do not have a more granular allocator yet. The only thing that we can use here is like page allocator. I mean, like theoretically, you could lean on like a standard library allocator to like make this guy, but let's just kind of say that we kind of want to keep everybody, we want to keep it all kind of, we want to keep our dependencies like clean, I guess, right? Like we're saying this guy needs a page allocator to do page allocations, but otherwise he shouldn't fucking need anyone, right? So given our constraints of one of these for the whole program, right? This guy plus this guy, I think means, that we can store each of these lists as like a linked list of pages, I think, right? So if we were to just get in like, we can imagine that like our 512 list, he's gonna have a bunch of pointers in here, right? He's gonna have pointer 1, pointer 2, pointer 3, pointer 4. You know, eventually we're gonna get to the point where he runs out of space, theoretically. And we're gonna have to like allocate a new page to store more pointers. I guess our constraint of freeze should be relatively rare probably means that we can get away with just like ripping an array up front. So we can probably just say like, yeah, okay, let's do this. We'll make this guy a function, and we're gonna say max free elms. Okay. We're gonna write our constraints here again, but I don't want to lose them. Okay, which means that we can say that we have free lists here is going to be one for each block size. So we know we can calculate the block sizes probably. So I think we were also going to say like min block log 2, I think. So first I think we can like calculate the page size. I think right now actually it's known at comp time. I think in the next version of Zig, this will no longer be comp time available, but we work on our current version of Zig. So I won't think about that right now, and we can always fix when we upgrade. But we know that we have like, you know, std math log 2 of these. So this is going to be log page size log 2. And so I think we know that we are going to have redundant comp time. Okay, we don't need it. Fine. We're gonna have page size log 2 minus min block log 2. These are how many free lists that we have. And in each free list, we have max free elms of pointer to U8s, I think. That's a nasty type. That is a disgusting, that's nasty, right? But we have, you know, one free list per block size. Each block size, we have some amount of stuff that we can fit, and in each one we store like a pointer. We don't have to store its size because we know that every pointer in this free list will have the size that is like it needs, right? Okay. And is that it? That's all the storage that we need, probably. We also need to keep track of our page allocator, which comes from these. Okay. So let's say that we implement the allocator interface for this. Boom. A page can be split into segments. Each segment has on position 0 its length with the last bit of the length can be the marker if it's free or not. Then you can iterate over everything without thinking. I don't think I want to do that. I think keeping them separate has like there are nice conveniences from that. I think. It means that when we allocate from these guys, all we have to do is pop the according block. So I think that makes like allocation really cheap. Where I think that if you made one big list with sizes, you would have to how do I say this? Dude, my brain's melting. You'd have to iterate the whole list, which I don't want to do. We want allocations to be like really cheap, and we're okay with taking a little bit of extra cost on freeze, which should be rare. I think that's just kind of like my current feeling, but you know, things change. Okay, so I guess each of these guys also needs list lens. So I guess we're gonna have like num lists is this, and then we can use num lists here and num lists of, you know, usize is probably overkill here. We're probably not gonna have that many, right? We could probably even get away with like u16, but I think again, since we only have one of these guys, it doesn't really matter. Okay, let's make our implementations of alloc free and resize. So what's going to happen here? On allocation, I guess we're going to make the assumption here that, okay, we need to figure out, given len, what is the which free list? So I think that's what align forward log2 does. No, that's not what this does. We want std math log2 int ceil. So we want to take the log2 of the length and round it up, I believe. So this should give us like log2 len, right? The block size that is like good enough. Then we say like free list is, I guess here we probably want to assert that the alignment of this guy is not like, is less than or equal to the log2 length, I think. Right, the idea here is that if this guy says 512 please, and our alignment is 1024 with align 1024, we're gonna like shit ourselves, right? Because that means that like we can't just pull from like the 512 list. We'd have to like walk it to find the right thing. So I think like the simpler thing to do here is just assume that the alignment will be less than or equal to like the log2 length. I don't know if that's true. I guess if somebody asks for like, you could imagine somebody asks for like a U8 that has to be aligned to 4-byte boundaries, but we're not really in that case. We don't have to think about that case, right? Because we're expecting like, you know, not like mega large allocations, but pretty large allocations. I don't think anybody should be expecting like a 128 block with a 128 byte block with 512 alignment. I don't think that should happen, especially with our usage. I don't think that will happen. We might find out that that's wrong later, which is why this assertion is going to be here. But I don't think it will come up. But we should make sure. So now all we have to do is we have to check if the free list for this guy has any elements. So if, I guess that means that we need self here, which is not this guy, it's a self. We're going to be like, if self list lens, I guess we need the list index is going to be log2 len minus min block log2. So if we're asking for the smallest block, we get 0, which is chill. And then I guess if log2 len is greater than or equal to page size log2, we fall back. We just like don't even touch ourselves. We just go like self page allocator raw alloc len pointer align ret adder. We just go, all right, this one's up to you, buddy. This one is up to you. Sure. Okay, so now then we check if the thing is available, right? So we say, I guess this calculation comes down here. If this is greater than 0, we're like fucking chill. So we say, you know, we go down by 1, and then we take the free lists at list index, and after we've subtracted, then that means if the length was 1, it is now 0, and we can use that as the index to go directly into this thing. So here we go to list lens at list index. And we just return that guy. And we've already subtracted, so we're chilling. Now, we don't have this thing, so it means that we have to like split someone above us. We need to like walk up the list. Split. I guess we want to be like alloc block at this list index. Or of log2 len. One of these. List index is probably fine. And we probably return this thing. Maybe we say like new page alloc for this list index. Okay. So this I feel like should be pretty straightforward. This guy's going to return this thing, right? And I guess we start. Well, we don't know that it's a new page yet. We don't know it's a new page yet. We know that we need to split a larger block. So I guess we need to like say split down, I guess, is fine. Alt F4 stream is just in chat saying touching yourself is a sin. I don't know why. I'm sure that I said something that triggered that, but it is also funny to think that you're just saying that because you feel like it. So here we're gonna take our list index. And I guess we're going to walk up. We're gonna walk up to the top list. So this is from this thing to the number of lists. And we already know that this list is empty. So we plus 1 here. That seems reasonable. So this is going to be like output list. And this is going to be the list index. Okay. Okay. So as we walk up, if we ever find a list that is not empty, which I guess naming feels kind of nice. Feels kind of nice. Which is just, I guess, this. Okay, so does it make more sense to do like a while loop here? While self is list empty, given this index, we increase index, right? We say, okay, then eventually we're going to know which index we're at. And I guess we should also say and index is less than num lists. Right? So we say while, I guess it's kind of the other way around. While index is less than num lists and the list is not and the list is empty, we keep going up. Right? So we're in our 256 block. We go nothing here, 512 block. Nothing here, 1024 block. We have a block here. Boom. Yes, love it. Right? So now at this point, we know which list to look at. So if index is equal to num lists, that means that there was nothing there for us, which means that we need a new page. So we're like, yo, page allocator. I guess we can get away with just doing like normal. Raw alloc feels fine. So we're like, give me, something of page size with alignment of, we'll just do a normal alloc. I'm sure that there's a reason to do raw alloc, but like, fuck it, this is fine. So we're gonna be like, give me something of std_mem page size. I'm not, I mean, that doesn't feel right. It doesn't feel right. Can we just pass in ret adder here? And then we can, yeah, okay. We can do this. So this is like, here is my new page. And then I guess we immediately split this guy in half. Yeah, so we immediately split this guy in half. And we put him in our maximum. We're going to put him in the free list, right? So we only really need to put one of them in the free list, though. So I'm trying to think, like, where does this converge back to what would happen in the happy path here? In the happy path, we would just say block is, we would like say that this is like pop index, or like, yeah, pop block at index. Or split block at index. Yeah, and then we would say like, while index is greater than output list, we like split block in half, insert into list index, and then keep going. I think that's what happens here. That feels right to me. So that means that this guy is equivalent to this split block. So I guess we're going to say get block for index, or pop. Yeah, I mean, pop block seems nice. I guess we can call it pop split or alloc block. Feels like a good name here. Yes, okay. And so now we take this guy, he goes down here. He's like, okay, we need a new page. We need a new page. And we split this block in half. So it's like, we take the page size over 2. And this is like, I I guess this is A. This is going to return something that could fail, right? So if this doesn't work, we're in trouble. And what is the thing that we're trying to return here? A pointer to a U8, probably? Yeah. Yeah. Okay. So this is like, if we don't get something out of here, we return error out of memory or something. Just kind of failed to alloc. Then B is A plus the page size over 2. Cool. Then we put one of these into the free list. So we're going to say like push block given some sort of like list index and a pointer. Okay. And presumably this can fail as well. So we're going to be like free lists at free list lengths. Free lists at list index. Okay. So this is this guy. Len is list lens at list index. Okay. Chill. Free list at len is equal to pointer, and len plus equals 1. So now we can push block here. And here we need to check first if len is equal to max free elms, then return error out of memory. Okay, cool. Yeah, that works. Then we push the block here. So we pushed like B into this guy, I guess. And then we return A. Seems good so far. I guess if this fails, we probably need to free this thing. So here, I guess we have like page align. Surely, oh, we already have this. We should just be using page size log 2 everywhere. So A, page size log 2, 0 to stdnem page size here. And then ret adder. Okay, something like this. Best part of my idea is you only need 3 pointers. One for the first page you allocate, and each page pointer is the next page. Yeah, I know, but I don't want to do it that way because I think that this is kind of more effective. I think less fragmentation, probably cheaper, so I'm okay with doing a little bit of extra work. No big dealio. I guess probably you could split. You're saying you could split the same way, which is fair. This is fine. Okay, so otherwise, we don't have to get a new page. And it just means that we are still going to get something and split it. Right? I don't know what we're going to do in the case where like a child list is free. I guess we just undo our action. So do we have pop block? No. but we can make one. So if we pop a block, we probably do this shit again. We're going to, I guess, say if len equals 0 unreachable, this shouldn't fucking happen. This should not happen. So we're just going to say that it shouldn't happen. And then here we say free list. We decrement the list. And then we get the value that was there before. And then we could even do, yeah, we could do one of these just for safety. We could do that. Fuck it. Okay. So now we can pop a block at list index. And then B is equal to A plus, list block size list IDX over 2. Or list index minus 1. Yeah. Which means that we just need like list block size here. And this is going to be 1 shifted left to, like, this is basically 2 to the power of list index plus min block log 2, I think. We should test this. Because I'm not 100% about this. We'll just do it now. Test block size calc. Tiny page alloc block size calc. Okay. So here we're going to say like const test type is tiny page allocator, and we're going to say that we have like 100 free elements, and the minimum block size is going to be 256. So like 2, 4, 8, 16, 32, 64, 128, 256, 8? I should know that 2 to the power of 8 is 256. I'm a fucking dumb piece of shit, okay? I get it. So here, we should be like list block size 0. This should be 256. And 1024 should be 1. And that's good enough. That's a good enough test. I assume that this won't compile for some reason. 918. I guess we can just assume that this will pass and we'll come back to it, right? We're assuming that this is correct. Okay, so when this is okay. And then we push block, and we return A. Cool. Cool. So, okay, what about here? If we fail, we just put it back. That seems pretty reasonable. So we just say, like, we know that A should go back there. Right? We're pretty fucking sure this should work, so catch unreachable here. Like, there's no world where we just popped this and we can't put it back, unless we've, like, really fucked up our code. Which means that this guy stays consistent, which is kind of hype. Okay, so now we're here. We find our index. We figure out which list we need to split. And as we basically just have to keep splitting this guy as we go down. So while index is greater than output list, we just say we need to Okay, so index here. Say that we're at like 4096 here. Index is still at 4096, so we probably want like index minus equals 1, which means that we're now in like the 2048 block, which means that we can do like list block size for index. We take the block plus index minus 1. So if this is, say we're at 4096 here, we're now trying to put into the 2048 block, so we need to, it's like this. Yeah, so we take this guy, we add 2048 to him, which is what index is now, and we put that. Push block this into index. And then at the end of this, I think we return block. I'm like not 100% sure here that we surely it's greater than or equal to here, right? I would assume that eventually we're going to be holding two 256 byte blocks, and we have to put one of them in the 256 byte list. But then we return the other one. Yeah. I think that's right. I think that's right. I mean, obviously we have to test this in some way. But that's like a maybe. That's not a no for me. Okay, so I guess let's do a sanity test here. Okay, so we're saying that we want 256 byte blocks. We have no more than 100 free elements per thing. We're gonna make one of these now. I think that we can kind of do it this way where we have these are equal to undefined off rip. No, we need an init function. We need an init function because we need to memset these guys. So, I don't really know. If you have like structs like this, I don't know if it's better to do like initialization inline or not. Like I don't really know what happens if I go like oh actually, you know what? I don't have to do it this way. We can do this at compile time, right? Surely. We can do like undefined times max free elms. And we're going to have, I think that this has to be in an array. So we're going to say like 1 pointer to U8 is undefined times max free elms. And then here we're going to have 1 max, 1 max free elms pointer to U8 times num lists. I think that that's right. I mean, obviously this is like a fix me, bro, what the fuck? I'm sure that there's like a better way to do this, but let's start there and then we can kind of like chip away at it. Then this is going to be 1 U size of 0 num lists times. And I think there's like, this gets like auto deduced at some point, but let's just kind of start here. Var alloc. Okay, surely this won't compile, but let's just kind of see where this takes us. No field name alloc. What is it called then? Page allocator. Fine, if you're gonna be like that. Error union is ignored at 103. Okay. 950. What was that? 954. It's probably something like this. Unable to cast runtime value to comp time int. Which one of these is mad? Yo, it seems like that could just be undefined. It does kind of feel like that, huh? Am I fucking stupid? Yeah, it does feel like that. You're right. You're very right. Okay, block size calc is wrong. So block size calc. So we expected 1024, found 512. Yeah, that's just true. I mean, we're just dumbasses. We're just dumbasses. Okay, so we construct now, and now we can try to do some stuff, right? So let's say that we try to alloc, you know, 256 bytes. Oh, we need to pull out the allocator interface, I guess. So this is just like pointer equals self, vtable is our allocator vtable, bing, bang, boom. Then down here where we use this guy, we say like page alloc, const alloc is page alloc allocator. Then we try to allocate a 256 byte block. And we are hoping to see one element in each of the lists, right? So we're trying to say that like page alloc for page alloc list lens. We're expecting each of these to be 1. We're expecting one block in literally all of them. What's it about? 894. Right, this has to be self because it's a function. And error union is discarded. True. Here. Raw alloc at 909. I guess we can just, what am I doing here? This is literally like return, right? Yeah. What about yellow pages? Am I having a boomer moment with that reference? Are tiny pages like a white pages thing? Or are you just saying like, are you just saying because that says pages? Expected 2 arguments on 1. Oh, I need the ret adder here probably. Okay, and then list block size. Is this thing like somewhat failable? No. Then what is, oh, this thing probably needs to be tried, probably? Yeah. Expected error union type found, yeah, 939. Right, because again, that's not how this fucking works. 950 list. We need pop block. Why can this fail? It can't. Push block at 931. He's mad about this. So, right, as we go down, as we like walk down our list, we go push, push, push. If we fail at one of these, we need to like unwind this whole thing. So I'm gonna put a fix me and say like unwind on failure, and then I'll just say like catch unreachable because I don't know what to do. I don't want to handle that right now. Okay. Integer overflow on split down. So that means this has to be greater than, because the minus equals happens every time. And then expected 1 found 2. So that's kind of interesting. That's interesting. It means that we have 2 blocks somewhere that I don't expect. Can we std debug print all of the list lens? One, 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 two. So that means that the first block that we allocated, this one, okay, so we must get to split down. And in split down, we get the first alloc block. Do we need to do an index minus equals 1 here? I think we do. There we go. 1, 1, 1, 1, baby. Okay, so now what do I expect? I expect that I allocate another one, right? I'm like, give me another 256 byte block. And what that should do, maybe we do like page alloc, maybe we do like a expect equal slices. So we expect 1, 1, 1, 1 for page alloc list lens off rip, right? Then we allocate another one, and we expect that to come out of the bottom block, right? So we kind of expect the 256 slice to be empty. We need to write down, I guess, usize here, probably. It's probably asking for the type of the things that we're doing lists of. And here we need some ampersands. All right. Yeah, okay, so that's working fine. Then we go again. And what should happen here is we take the 512 block, we take it out, we put one of the halves in the 256 byte block, and then we're chilling, which is working. Hell yeah. Okay, so then let's say that we try allocating a 1024 byte block. That comes from this guy, so this comes to 0. Okay, okay. And then let's try to do something that requires, a little bit of shuffling. So let's try to do a 512 byte block. This guy gets split in half, then another one goes in here, and another one goes in here. Yeah, that's working great. That's working great. So allocation side feels like, assuming that the pointers are also correct, feels like it's working correctly. We're making a pretty big assumption there, but I think it's fine. Now that you're working with page subsets, do you think there could be some scenarios where CPU cache comes into play? I don't really know how that works. Yeah, but I think that any scenario where that would be relevant, we would just fix by allocating a better chunk up front, right? Like, the only time, so these blocks, like, the only time you would be using a 256 byte block is if you have an allocation of less than 256 bytes, in which case, like, the caching doesn't really matter, I don't think. I think you typically expect pointers to kind of be scattered around the system. Like, that's just kind of the expectation that I have. Our bump allocator will not be moving as linearly anymore, but I was going to kind of solve that by having the bump allocator start by allocating a small page and work its way up to allocating like full real pages. So that like we should only ever have like a small amount of allocations at this like small page size thing. I think that was where I was going to work towards. Okay, so I guess that's like allocation. And so I guess we can kind of say here now that we're kind of working on free. Tiny page free. Okay. Okay. So resize, we're just going to return false, I think. We're just not going to support that right now. We might support it later. But this is just kind of simpler for the time being. And then free is kind of the fun part here. Okay, so first we figure out which block that we're in, which should be std math log2 int ceil of buff line, right? We're chilling there. And in reality, the buff length should always be a power of 2, but you know, just in case. We're gonna ignore alignment because that doesn't play a part in our thing at all. And we are going to start by just putting the thing into the block. I guess we're gonna say, so this is our index here. We are going to first check if there is a sibling in that block. So if free lists, I guess like self has sibling for this pointer at this index. I guess it's probably while this index goes up by 1 and we pop the block out of that index, right? So we say like while has sibling, this will give us like the sibling index like this. And we will say like self swap remove for list index index sibling index sibling index. Okay, yep. So we're gonna like swap remove that thing. Var lock point, like pointer is going to be buff pointer here, I think. And when we pull this guy out, we're going to presumably take the minimum of the two, right? Because like if we have, you know, we're some number, we're pointer A, right? And in our list we have, okay, so there's A and B. A and B, these are the two siblings, right? We could be B and we say we have a sibling A, great. This is the pointer for our parent block, right? It's never this because this is halfway into like the group of a parent. So we should always take the smaller of the two. I think that's correct. I think that's correct. Then we go up a list level. Okay, then if index, if we've made it all the way to the number of lists, we should release this thing back to the page allocator. Right, so we should be here and we should go like buff pointer from 0 to std probably page size here. I don't think we're ever allocating something bigger than one page and putting it into our free list. That shouldn't be happening. Buff align should just be log2 page size, and ret adder, I guess we just use the ret adder that was passed in. I think that's fair. I think. Then, otherwise, we push this block into this list index. And then we should say while yeah, I think that's fair. I don't want to deal with this right now, so I'm just going to catch unreachable and put fix me surely, like Yeah, I guess that really is unreachable. We can't recover. I don't see how we can recover. The list literally isn't big enough. Um, yeah, I guess in release mode we like warn about a leak or something. Is probably the best we can do. But otherwise, does this feel kind of right? So here we have to check. We used to implement head sibling. So here we take in our self. We have the pointer. And we have the list index here. Yes. And we're going to return an optional index into the list. So we're going to say for 0 to the free, like the list lengths at list index, right? List len. No. Free lists. For 0 to list index. That makes more sense. No, wait, we know we're only looking at one list. I'm a dumbass. So yeah, we go for this, and we get an index here, and we say self free lists at list index I. If okay, so I guess we want to check. We probably want to know like if the pointer is like yeah. How do we determine if we're a sibling? It's if we shift right and they have the same address. Yeah. So if this is equal to compare, so we'll write down here like shifting right by 1 drops the lowest bit, which means that we will that 0b00 like xxxx1 and 0b xxx0 will only match if xxxx equals y. Yep. Yeah, I think that's fair. I think that works. So this means that we return I, and then here we return null. Okay. That's a maybe. Then we need swap remove. So this is going to take the list index and the sub index, I guess. So we're going to look at self free lists list index. So we're going to say like free list is self free lists list index like this, right? Then we have const len is self list lens at list index. Then we say eventually len is going to be minus equal to 1, and all we have to do is take the thing at free list at sub index is equal to free list at len after we do this. So we take the thing at the end, we put it where the thing we're trying to remove is, and we like do then we're donezo. That's kind of like the swap remove. Then this returns void. Seems kind of reasonable to me. Then there might be a special case of sub index is the last element, but this is just a self assignment, which I think is fine. Probably we might need to dodge that, but for now it feels okay. Okay. Log2 int seal. This guy needs to say that he's Doing this with usizes. Okay, so we can't take the minimum of these, but with at min. But can we just do pointer is equal to if pointer is less than other, pointer else other? I mean, we also don't have to do this, right? We know that this is going to be, we know that we can just drop. No, we don't know this. Also, this is wrong. Lowest bit is not, we need to shift by more than 1 here. Shift amount is equal to what? Min block log 2. This minus this, right? So that feels kind of right. That feels kind of right. Okay. I think we'll just keep doing it this way. That feels nicer. Swap remove, and this returns wait. So here we say const ret is free list at sub index, and then we return ret. All right. Can't compare these, really? As usize int from pointer. It's kind of annoying. That's annoying, but we'll make it work. Oopsies. Let's see how that works. Pointer from int. Okay. Bit shifting can't be done from these, so can we do like const pointer u32? Or not usize, sorry. Actually, does int from pointer derive the type? It might. Const list val is, you know, int from pointer here, and then we can do list val here. Close. Shift amount is pissed off because, like, you know, he might be shifting more than can be shiftable, but whatever. Okay, cool. Compiles. So now we can try freeing something and see what happens, right? So we expect that if we free this block, right, the last block that we allocated, we should go back to this state, right? Right? If we like, it must, right? We take the 512 block. He goes, uh-oh, gotta merge this. Yeah, we merge this one, then we merge this one, and we have this one at the top, which is not working. So why? Index out of bounds. List index is 9, which means that we've done something like brain dead fucking stupid. It's that Shirley has sibling needs to subtract the min block log 2 to get offset correctly. Okay. Integer overflow. At shift amount. I think it's plus here, not minus. Okay. So it looks like we did, in fact, get this guy into the list here, right? We put the 512 block back in, but he didn't successfully merge himself, right? So I'd be curious to maybe take a look at this as sibling. Oopsies. And kind of just see, this is maybe we breakpoint here and we just kind of see what's going on there. Okay. Okay. So wait, that's okay. Print pointer. Okay, so we got this thing and we shifted right by presumably 8. Arithmetic operation to not a number or a boolean, really? Can we do usi, like U64 pointer? How do we cast this? Can you like cast a GB? Can I do like uint64t? Key U32? Ugh. God damn it. I guess we just do this. We just open Python. We do it by hand. Because I don't know how. I don't know how. I mean, wait, but shifting by 8 should get us something that resembles the thing, right? So we know that we're not shifting by 8. We're shifting by 9. Which makes sense because we're on the 512 block. Okay, that makes sense. So can we take this thing and shift it right by 8 or 9? And then can we print as a hex number like this? How do I, like this? There we go. B4. So this does look like the right number, right? These are the same. So that's good. So can we now look at like free lists? We want to look at the second free list. This is not working the way I wanted it to. What is happening here? Why is this like fucking up all over the place? It just looks fucked up. Fuck. Okay. Let's breakpoint here. Yeah, like what is oh, is it running multiple tests at the same time? Can I like filter these tests by like can I run like can I ask it to only run this? Like if I do this, is he happy? Unrecognized command line argument. Only listen. So I can't filter by like a single test? Can I run zig test with like I can do a filter? So can I just say like this? Okay, and then can I GDB this? Like, does that work if I do this? He builds it and then runs it. No, I'm not so lucky. But it does look like this thing exists. Um, It does say 1 passed, 0 skipped. Where, like, when I do this, it says 1 passed, 0 skipped, 1 failed. Oh, so maybe the test filter should be like this guy? Oh, there we go. Here we go. So now if I run this, is it the same? It is. Nice. Okay. Okay. It's still doing it, though. It's still fucking doing it. Which is annoying. Like, whatever. List val. Whoa. The fuck? There's no way that... that's right. There's no way that's right. Okay, we're falling back on I don't trust GDB right now. Okay. And we'll just use good old logging. We'll just use good old logging. Can we print this as hex? Can we print this as pointer? Sure. Okay, so we have this guy. And this guy. Which do seem not like siblings. Well, they might be. They do have the first some amount of bits. Okay. They have some amount of bits in common. So can we do like binary format this thing? We have this guy. This should be like this and this guy. One, two, three, four, five, six, seven, eight, 9. Am I off by 1 here? I think I am. I think we want to check if one layer up. I think that this has to be +1. Yeah. Nice. Okay. So now we can just start trying to like work our way backwards. So okay, so then we free this 1024 block. And we should go back to this state. No. This state. If we free block 2 here. Okay, and then we can just kind of do the rest out of order. Block 3, block 4, block 5, and let's free them in some arbitrary order. So maybe we'll do like, 4, 5, 3, right? And now we should find that all of these guys at the end of this are all 0 because everything has been reclaimed. Which is not working. Not working. So this is at 1039. He's mad probably because the list index can get out of range. So at some point, we need to say if list index is greater than or equal to num list, return false. And then can we print here that we're freeing list, like actually freeing? Return null, I guess. Okay, so we do see actually freeing and all the tests pass. So I think this is working. Shift right by, shift right, shift all bits, shift right until we only have the bits that represent our parent. There we go. Siblings will have the same leading bits. Okay, so this sounds like it's working. Hand wavy. It would be interesting to test this thing. Oh, okay. I guess the question now becomes like, how do we use this thing? I guess we integrate it with our sphalloc, right? So here we have this block allocator who has page-sized linked lists of blocks. And he probably hard codes the page allocator in here, which isn't good. We need to replace this with our allocator. Okay. So backing alloc. Yeah. And presumably here, we also need to tell him what like the minimum block size is. Presumably. So he's using studmem page size all over the place. I guess we should know this at compile time. Probably. And if we do this, right, we are technically increasing the cost of every single like memory pool that we create. You could argue that all of these guys should know exactly who they're talking about, right? And you could make some global do that. I don't really want to do it that way. I'm okay with doing this for now. Page alloc here. This is fine. Maybe a little suboptimal, but not the end of the world. Not the end of the world at all. Okay. So page alloc is equal to page alloc here, and we... Oh, I guess he's technically stored in here, huh? No, he's not. Is this guy using the page allocator directly? Oh, it's on insert, I see. We're passing him in on insert. So this guy knows that he can use whatever. That's great. Okay, so now basically everywhere in here where we have a page allocator, this turns into self page alloc. Okay. Cool. So now when we initialize this guy, we take in our page allocator. Okay. And now this guy needs to make one of these guys. So var page alloc is going to be like sphalloc tiny page allocator. And we're going to say we can have like 100 free elements and min block size of, 256. Okay, and now we have to make sure that everything related to this guy that needs to be public is in fact public. But we actually did just say that we do like page allocator stood heap page allocator like this. Okay. Then here we use page allocator. Then this guy, we need to give him the same treatment. Okay, now, oops, this is backwards. Backwards. All right. Then when we create sub guys, we should just be able to keep using like self block alloc page alloc or something. Kind of get that for free. On reset, we reinitialize this guy. I'm not 100% sure on this, but whatever. Okay, so I guess now the question becomes, does everything still work? Oops. Does everything still work? No. Why? Because we're hitting a case where integer overflowing on the log2 length of this guy is less than the minimum block length. Interesting. So that means that they are asking for something that is too small, which I don't think should happen. I don't think that should be happening, right? As far as I understand, no one should be fucking asking for something that's smaller than a page at this point in time. So let's try to figure out who the fuck is doing that and why. Because whatever they're doing, fucking rude, dude. So this is coming from general purpose allocator. Is ending up asking us for something with a length of 120. Interesting. Okay. So, okay, we can fix this for now. For now, if we reroute the general purpose allocator through the bump allocator, then we should know that nothing should ever be too small. I mean, that'll fuck things up a little bit because we're going to end up with some like wasted memory. But that should at least unlock testing for us. It should. So can we do that? Can we say that the general purpose allocator here uses wait a second. This doesn't look right. This was not doing the right thing. We're supposed to be doing this here. Which, I mean, isn't really our problem, but it is annoying. Okay, so what if we do this? Does that at least fix the crashes? Because then nobody should be asking us for something that they can't use. Okay, so now we have some free list issues here at 980. So here we are sometimes trying to push a block for something that's out of bounds. So that must be coming from that must be coming out from free, right? Yeah, it is coming from free. And what have we done wrong? So this is on here. Index 5. What is num lists? Am I high? Oh, num list is 4. Oh, so this is like if it's bigger than, right. That makes sense. That makes sense. If somebody has asked us for something that's even, like, not, we don't just support only allocating at exactly the page size, but also if it's bigger than. That makes sense. Yeah. Where was that? That was on free. Here. So I guess we could like short circuit this case here as well, but I think it'll just kind of work out. Okay, so now what's happening? Raw alloc is returning out of memory. Oh, that's kind of interesting. That's interesting. So that means that, like, okay, let's just, bump it up an order of magnitude. See if that kind of helps out. Even that is not enough. Interesting. Interesting. So can we look for on allocate here? Can we breakpoint here? What the fuck is going on here? Clearly, one of our constraints was not true, right? Clearly, if we're hitting 1,000 elements in the free list, we're doing something fucking wrong. But that's not it. Whoa. Then what is? This is an allocate, right? Yeah. It is. So it would have to be this one. No? Am I stupid? Somebody is running out of memory. Or someone is failing to get new memory, right? They're calling raw alloc. I guess it could be. I guess what we should do. There is another guy between us. There's the block allocator. Who can return null here. But shouldn't. Like, this should just be using our guy under the hood. So I don't see any reason why this would change anything, but we might as well check. Yeah, very strange. Very, very strange. I guess there could be like some corruption. Could be. It could be this like self-reference shit we were doing. Okay, I'm just going to try this. Not that I think it matters, but I'm confused that we're like not seeing. Yeah, I would just love to see where the problem is. You know, can we like how far? Okay, what if we just breakpoint kind of willy-nilly? Willy-nilly, we just hard breakpoint. Okay, so makes sense. Makes sense. There's tons of people allocating. They're allocating, they're schmallocating. I guess technically he's going through the arena now as well. Which I did kind of forget about. So it could be that we have an out of memory in our arena allocator as well. It's a very real possibility. I just want to make sure that I remember to put this back to where it was supposed to be. I did. Okay, so our... Oh! I'm a dumbass. I'm a dumbass. I forgot that we lock our arena. Intentionally. We were like, yo, don't fucking allocate anything for this guy. And then we said, wait, but all of our all of our general purpose allocations go through the arena that's locked. So like, of course this is gonna happen. Okay, wait, I think that maybe things are just kind of working. I forgot. Okay, break point. Break point. Maybe it works then. Oh, we're up. We're up and running, baby. So that's pretty hype. That's pretty hype. And it looks like memory usage is still reasonably sane. And what we could do is we could delete a bunch of objects here and see what our like object storage overhead is. 16 kilobytes still. Right? So that kind of makes sense because everybody is using this tiny allocator under the hood, but nobody is like actually like using his capabilities, if that makes sense. Like if we look at frame 6 here and we print what the fuck? Oh, it's page allocator. Right? We do see that there is nobody like there are no free elements in here. I guess that doesn't really prove a lot. But we could go into Tinypage allocator here and just write down if anybody is ever actually requesting a small allocation. Right? So in here we could print here. Right? Std debug print small allocation requested. Right? And I'm assuming that we're not going to see that. Yeah, I don't see anywhere in here that says small allocation. So that kind of makes sense, right? So now what I want to do is I want to go into our bump allocator here, and he now should be allowed to allocate smaller elements, right? So here he's kind of hard coding the page size, but I guess what we can do is give him a comp time value of like min page log 2. Yes. And then everything he did before, he's just like returned. And then wherever he uses stood mem page size in here, we're going to replace with min page. We have to be careful. So here we want like min page size is equal to 1 shifted left by min page log 2. Then in here we can go anything that says stood mem page size uses min page size. And then we don't need anything that's like log 2 min page size is just min page log 2. Okay. Cool. So I guess we're kind of working on this now. We're kind of working on this. Okay, so now our bump allocator here needs to... I'm going to do this at runtime. It's just easier to pipe everything around that way. Min page, like, min page log 2. It's just easier. It's just easier. Okay. So here he's like, give me our block alloc of block alloc and our min page log 2. I guess he doesn't really need that in it. That's going to come for free. Okay, so who's making these bump allocators? It's got to be just in like sphalloc. This guy's probably who's making them. So here he's got min page log 2 is equal to min page log 2, I guess. If this belongs here, that makes sense. What is this going? Self storage arena. Okay. We'll kind of pass it along like that. Then everybody's mad that we're like not using the right min page size here. So for now, we just kind of slap an 8 in here and we'll come back to it later. Where does this come from? It comes from arena inner min page. There we go. This is like we're hacking, right? I understand that. What version of this? Already 0.14? I'm on 0.13. I didn't know 0.14 was out yet. It's kind of hype. Okay, so strangely, it doesn't really feel like that's working. I would have expected to see those logs, unless I forgot to leave them in. No, so I'm still not seeing any small allocation requested logs, which I was kind of hoping to see if our bump allocator supported small allocations, right? What if we like off rip try to force one, right? If we're just like root alloc arena allocate like 8 bytes. Come on, you gotta tell me. You gotta tell me that that uses the small alloc. It's gotta. No. Okay, so what's going on here? What the fuck is going on here? Can we breakpoint here and just like take a little peek ski because obviously something is not doing what I expect. Okay. So we go in here, blah, blah, blah. We jump down. Eventually, somebody is going to end up in our root allocator somewhere. We just got to figure out when that's going to be. So here, raw allocate. Okay. So now we're in the lockable arena, which goes into the bump allocator, which goes into, I hope, somewhere. We'll see. Blah, blah, blah. Alignment stuff. Alignment stuff. Alignment stuff. Okay. So yeah, okay. So this stuff should not work. Then we align forward. Eventually some power of 2 shit. Alignment stuff. Alignment stuff. Okay, can we get out of this fucking insertion, please? Okay, here we go. We go into our block allocator, and we are trying to allocate with a length of 8, right? So what is our block length here? 4096? The fuck? God damn it. I forgot to make the change that we needed. Everybody in here is still using Studman page size. This should be self page size, maybe? And then we need like page size here. Oops. Function page size is bump alloc returns a u size, and it's 1 shifted left by self min page log 2. Okay. Then this is self min page log 2 like this. All right. That makes a lot more sense. Way more sense. Okay, incorrect alignment. Okay. Full block length here at 767. So this is in block allocator. What are we even trying to align here? Allocated blocks. What is happening here? So we allocate something in here. We go, okay, here's our page allocator. We want to insert a value into this thing, where value is a block. Blocks are expected to be aligned to the page size now, and that's no longer true because we're supporting Tinypages now. So that align cast is rightfully failing because he's got a block that's too small. And he's going like, what the fuck? That doesn't fucking fit. Okay. So now we're hitting this case where our alignment constraints are not true. So why is that happening? This is at frame 7. So this alignment is 12 aligned. Oh, sure. So this alignment, they're asking for page alignment on this thing. And we're like, wait, but that's bigger than our like small page alignment, wherever the fuck that was. write this. So I guess it's probably fine. I guess like we need to make sure that like effective alignment is going to be like the larger version of like the pointer alignment or the length. And that's not really this guy's job to check that. That's kind of more on our tiny page allocator. He needs to validate that. Which he does. So I think we're chilling. I think everybody's happy there. Okay, so now we have a bunch of small allocations requested, which is hype. And if we go into our main, or I guess this main, the other main, and we look at the page allocator here, we do see that there have been lots of small allocations requested, but there is literally only one small allocation in the entire application that is like in the free list, which is kind of lines up with our expectations. Uh-oh, this isn't good. There's an align cast in our page allocator. Free all memory. Okay, let's take a look at that. It looks like it's possible that this guy is expecting to use the wrong allocator. Doesn't really feel like. So how are we getting to M on map here? Block alloc dnit, page alloc free block at 732. And somehow this guy is getting the wrong allocator? Because this is now going into page allocator, which feels fucking wrong. So like, how the fuck is that happening? He should be going through tiny page allocator. Keep page allocator. Is there like, yeah, nobody should be doing that. Unless this backtrace is wrong. Let's take a little peek skis. So what do we just clicked on something else? And we look at our backtrace and we go to, oh yeah, okay, we're at frame 8. We are in our tiny page allocator. And okay, so what's happening here? So we're at 1031, which is this. So we have that the index here is 4. And so we're trying to free the page that we got. That makes sense. Oh, but is the page size wrong here? Alignment is wrong. Yeah, he's definitely not, he doesn't feel like he's aligned to a page here. It feels like we should be seeing 600 here. Right? What's 4096 in hex? Yeah. So this is not aligned correctly, which is true. Which is true. So how the fuck is this happening? We did get a buffer. We did say this guy has a length 4096. And so how could we have gotten a thing of 4096? Is it like our block allocator is doing something fucking stupid? Let's take a little peek. He might be like assuming that he can merge blocks when he can't anymore. Like, yeah, my suspicion here is that the block allocator is trying to merge blocks or something when he shouldn't. Although I don't see that happening. I don't see that happening. But it's pretty clear that in his storage, he has a thing that's like not aligned correctly. This is maybe the problem. This is the problem. So he's assuming that everything is going to be at least a page size, and that is no longer true. So we need to insert the thing of the correct length, which means that our block allocator needs to know the min page size so that here he can align forward according to that. And then here, we have another test here. What's going on here? ln is greater than, yeah, min page size, I guess. He was making assumptions everywhere that like we were using like an actual page size here. Min page log 2, and then we say page size equals 1, shift left by min page log 2. Okay. Then when we initialize this guy, we need to initialize him with min page log 2 on both of these. All right. And then again, he's pissed off about like as usize 1 and incast here probably. And then this I guess is a U8 probably. Okay. All right, we're so back, baby. And now that we've kind of like poked around a little bit, what does our thing look like? We still have basically no small allocations left over, which is pretty hype. Pretty hype. We could also maybe look at some like block allocator sizes. But we can come back to that. All right. I think yeah, let's just look at I would love to look at the block allocator as well. So these guys are the guys who's like in charge of like writing down which pages have been allocated. Presumably he's going to have like a lot of small allocations left in here now. So can we maybe print every time we free maybe? Or every time we allocate? Can we just print the size of this thing? How many allocated blocks are there? What is this thing? Page linked lists. What does this thing do? He's got like a next in here. So I guess we iterate them and add them up. Yeah. So if we want to calculate like number of elements that we have in here, we can do that by saying num elements. And he gets like an iterator. What does this thing give me? This is a stupid way to do it, but it's fine. All right. Okay, what's he mad about now? Invalid format string. Oh, because I didn't actually finish this log. Self-allocated blocks, len, here. This is going to slow everything down. It's a really inefficient way to do this, but I just want to see the answer. Yeah, okay, so we are getting into like 65 in some cases, right? Which isn't ideal. Right, so it would be nice if our bump allocator kind of like accelerated, right? That'd be kind of hype. So I think that what we can do is every time we allocate here, we can just say, I guess we shouldn't change this. Alloc size log2, and every time we allocate, we double it. And I guess it's like we're gonna say that equals to the maximum of 12 or alloc size log2 plus 1 or something, right? And then here we use alloc page log2, and then I think we're kind of chilling. So that should make it so that we go like small block, bigger block, bigger block, bigger block, and hopefully the amount of small pages then kind of reduces as a result of that. Yeah. Okay, so 1151, we want, you know, this guy to kind of start out at the small size. Probably max, not min, not max. Yep. Thank you. Every time I want the maximum value to be this, which is the minimum of the two. Every goddamn time. Okay, so we do see that like kind of the number of allocated blocks has dropped now. We were seeing stuff in like the 60s before, and now we're kind of seeing it stay relatively small. One of these guys is getting a little large, right? He has kind of like 30 of them. But it's really not the end of the world. Really not the end of the world. Okay, cool. So I suspect that the general overhead of these things is still relatively high, because we have to get a little bit better about, we probably have to like refactor the general purpose allocator out a little bit, right? The general purpose allocator is kind of expecting to use page sizes still. So I suspect that like something that is very similar to our tiny page allocator, right? That uses this like buddy size thing, right? This guy has like a block allocator from the range of like 256, 512, 1024, right? 2048 or whatever. This is like what he has. We just need like our general purpose allocators now. They don't have to care about anything in this range. And then we can kind of make one that goes from like 8, 16, 32, 64, right? Something like relatively simple that sits below here, and replace the general purpose allocator usage with this, which should again be like relatively simple. The constraints on this guy are going to be a little different, right? So we had like these rules of like, you know, allocations will be powers of 2, frees will be relatively rare, allocations, like we're optimizing for allocations. It could be that in the smaller half of these things, we're going to make different trade-offs, right? So we might want something a little bit more specific, but that's a problem for another day. So I think we call it there. I would say this is a success. We definitely have the ability to allocate small pages now. In fact, Maybe we even write down a little bit. Maybe we even write down what the block. When we look at the blocks, I would be a little bit interested to see in our current form. Where was it? This guy. Can we say, for each block, can we look at them? I'd be curious to see like what their sizes are. You know? Var iterator is equal to self allocated blocks iter while it next. And then we can say we have a block of size this. Let's just kind of see what's like a typical allocation size here. Are we seeing like a lot of the small ones, a lot of the big ones? Like what's going on here? Right, so we're seeing still the vast majority of blocks are, you know, over a page. But now we do see occasional blocks that are a little smaller, which is kind of hype. Kind of hype. All right, so I think shit's working. Pretty happy with that. Thanks for watching, guys. If you like what we saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 4 o'clock Pacific time now, so anywhere between 3.5 hours ago and now. If you're watching live, there's a YouTube link in the Twitch description where you can keep up with this stuff. This stuff will probably go under there. I think we have a memory allocators playlist, which is where this will live. I'm hoping to be kind of done with this stuff soon, so back onto maybe some more, proper feature development. But I think I need one more day at least of trying to patch up the general purpose allocator. But we will see. Otherwise, thanks for watching. YouTube, peace out. Twitch, let's find someone to raid.